Hey folks, this is Alice from Knowithere team. In this episode, we will talk about the great theory of Albert Einstein, that is the theory of relativity. Source: Wikipedia. The theory of relativity usually encompasses two interrelated theories by Albert Einstein: special relativity and general relativity. Special relativity applies to elementary particles and their interactions, describing all their physical phenomena except gravity. General relativity explains the law of gravitation and its relation to other forces of nature. It applies to the cosmological and astrophysical realm, including astronomy. The theory transformed theoretical physics and astronomy during the 20th century, superseding a 200-year-old theory of mechanics created primarily by Isaac Newton. It introduced concepts including space-time as a unified entity of space and time, relativity of simultaneity, kinematic and gravitational time dilation, and length contraction. In the field of physics, relativity improved the science of elementary particles and their fundamental interactions, along with ushering in the nuclear age. With relativity, cosmology and astrophysics predicted extraordinary astronomical phenomena such as neutron stars, black holes, and gravitational waves. Development and acceptance. Albert Einstein published the theory of special relativity in 1905, building on many theoretical results and empirical findings obtained by Albert A. Michelson, Hendrik Lorentz, Henri Poincaré and others. Max Planck, Hermann Minkowski and others did subsequent work. Einstein developed general relativity between 1907 and 1915, with contributions by many others after 1915. The final form of general relativity was published in 1916. The term theory of relativity was based on the expression relative theory, German, relative theory, used in 1906 by Planck, who emphasized how the theory uses the principle of relativity. In the discussion section of the same paper, Alfred Butterer used for the first time the expression theory of relativity. By the 1920s, the physics community understood and accepted special relativity. It rapidly became a significant and necessary tool for theorists and experimentalists in the new fields of atomic physics, nuclear physics, and quantum mechanics. By comparison, general relativity did not appear to be as useful, beyond making minor corrections to predictions of Newtonian gravitation theory. It seemed to offer little potential for experimental test, as most of its assertions were on an astronomical scale. Its mathematics of general relativity seemed difficult and fully understandable only by a small number of people. Around 1960, general relativity became central to physics and astronomy. New mathematical techniques to apply to general relativity streamlined calculations and made its concepts more easily visualized. As astronomical phenomena were discovered, such as quasars, the 3 Kelvin microwave background radiation, pulsars, and the first black hole candidates, the theory explained their attributes, and measurement of them further confirmed the theory. Let's discuss about both the theory. First, special relativity. Special relativity is a theory of the structure of space-time. It was introduced in Einstein's 1905 paper on the electrodynamics of moving bodies. For the contributions of many other physicists, see History of Special Relativity. Special relativity is based on two postulates which are contradictory in classical mechanics. The laws of physics are the same for all observers in uniform motion relative to one another. The speed of light in a vacuum is the same for all observers, regardless of their relative motion or of the motion of the light source. The resultant theory copes with experiment better than classical mechanics. For instance, postulate 2 explains the results of the Michelson-Morley experiment. Moreover, the theory has many surprising and counterintuitive consequences. Some of these are: relativity of simultaneity. Two events, simultaneous for one observer, may not be simultaneous for another observer if the observers are in relative motion. Time dilation. Moving clocks are measured to tick more slowly than an observer's stationary clock. Relativistic mass. Length contraction. Objects are measured to be shortened in the direction that they are moving with respect to the observer. Mass-energy equivalence, E equals mc square, energy and mass are equivalent and transmutable. Maximum speed is finite, no physical object, message or field line can travel faster than the speed of light in a vacuum. The effect of gravity can only travel through space at the speed of light, not faster or instantaneously. The defining feature of special relativity is the replacement of the Galilean transformations of classical mechanics by the Lorentz transformation. Second, general relativity. General relativity is a theory of gravitation developed by Einstein in the years 1907 to 1915. The development of general relativity began with the equivalence principle, under which the states of accelerated motion and being at rest in a gravitational field are physically identical. The upshot of this is that free fall is inertial motion. An object in free fall is falling because that is how objects move when there is no force being exerted on them, instead of this being due to the force of gravity, as is the case in classical mechanics. This is incompatible with classical mechanics and special relativity because in those theories initially moving objects cannot accelerate with respect to each other, but objects in free fall do so. To resolve this difficulty, Einstein first proposed that spacetime is curved. In 1915, he devised the Einstein field equations which relate the curvature of spacetime with the mass, energy, and any momentum within it. Some of the consequences of general relativity are: clocks run slower in deeper gravitational wells. This is called gravitational time dilation. Orbits process in a way unexpected in Newton's theory of gravity. This has been observed in the orbit of Mercury and in binary pulsars. Rays of light bend in the presence of a gravitational field. Rotating masses drag along the space-time around them, a phenomenon termed frame dragging. The universe is expanding, and the far parts of it are moving away from us faster than the speed of light. Technically, general relativity is a theory of gravitation whose defining feature is its use of the Einstein field equations. The solutions of the field equations are metric tensors which define the topology of the space-time and how objects move initially. This is it, folks. Stay tuned for more episode from Knowithere team. Have a great day.